Well, this is Mark Unkefer. I'm director of the Fiber Optic Sensing Association, and I'm welcoming you to our monthly webinar. This month, we're very privileged to have Dr. Alex Philp of Adelos. Each month, we've been highlighting a number of the specific applications that fiber optic sensing can be used in. We've addressed pipelines and rail. In this month, we're able to highlight a rather innovative system that Adelos is pioneering in the space of integrating systems together within a IoT-centric network of system or system of systems optic sensing, optic sensor engineering as Adelos describes it. So, Doctor, we're very privileged to have you here and look forward to hearing your presentation.
Thank you very much, Mark. I appreciate it, and it's good to be here this afternoon. Welcome to all of our attendees. Adelos is a proud member of the Fiber Optic Sensing Association, and as my role at Adelos, I'm the Chief Technology Officer and founder. And what I'm going to focus on today, as Mark related, is really the notion of how distributed acoustic sensors or fiber optic sensing systems can work together and do work together with other sensors to achieve greater situational awareness, greater intelligence, greater insight on a variety of phenomena. But where we focus at Adelos is in the defense intel space, U.S. government work. And so what I was able to do for FOSA, with FOSA, and bring to the audience today are a series of examples of things that we've done for different elements of the U.S. government. So this is, in that sense, it's going to be high level, but I'm going to really try to highlight how things are connected. So the first thing I want everybody to know, and I just need to get this on the table, is that Adelos, the company, is part of a larger group of businesses located here in Montana, which are part of the Confederated Salish and Kootenai Indian nations, the Confederated Nations. So we are part of a group of tribally owned companies. We are tribally owned, that are Native American, that do world-class work around the United States and actually internationally. And it's kind of a unique business model that I doubt is known very much, and certainly a unique part of FOSA membership. But we report up to S&K Technologies, and our sister companies are involved in aerospace for U.S. government, engineering and research, solution architectures, logistics services, and we build and manufacture and sell the photonic sensor. So I'm calling in today from Missoula, Montana, and just to the north is the homeland of the Confederated Salish Kootenai, and we represent one of their strategic investments. I'm not going to go into too much detail about this because that's not the point about fiber optic arrays and cabling systems and sensor systems. Suffice to say that we have one. It's called Phosonic. There's a picture of it. We really work very hard to optimize our particular sensing array and work very closely with cabling manufacturers, fiber optic cabling manufacturers, regarding the relationship. And I wanted everybody to know that, you know, our sensors are virtual. They live in the fiber optic array, buried in the ground, et cetera. But we really like to let people know that when you're doing this kind of sensing, what's in the ground really matters. And, you know, how do you optimize for the physics is really a soup to nuts thing that we worry about. So those are our boxes. That's what we sell. And we've been privileged, I guess, over the years to have a series of very interesting challenges and problems given to us by the U.S. government in security space. So you'll see a lot of that in my presentation today, as I said earlier. So distributed acoustic sensor systems, security applications. So what you guys are going to be exposed to during my presentation today is really kind of a persistent concept of defense in depth. So, you know, typically, not only are fiber optic sensors used, but you're talking about integrating with camera systems, with infrared systems, with hydrophones, with geophones, with seismometers, with accelerometers. You know, a lot of different sensor systems that are increasingly becoming part of a network. So you have this whole idea of the growing Internet of Things architecture. And so I'll be addressing perimeter border infrastructure and even cybersecurity. And you may wonder, well, how is that relevant? Well, as we all know, there's an increasing layer of attack where you can do things in cyberspace and cause physical events to occur. We're going to see that more and more, unfortunately, as infrastructure is attacked, as buildings are compromised, as cars are compromised, and sooner or later, fiber optic sensing systems are going to be part of that overall security stance. When I say system of systems, some people like that, some people don't. But generally, we never do a project for any of these kind of customers here, the Navy, the DOE, whatever, unless we are integrating with, adding value to other sensors. And the idea being that no single sensor system, as far as I'm concerned, is able to address 100% of the security problem, the intelligence problem, the surveillance problem, or the recon problem. And I'm not here to lecture about MASINT, but if you think about measurements and signals intelligence, MASINT, it's really important for FOSA members and, more importantly, FOSA advocates and the audience today to be thinking about how sensors are not only telling things to do things like, oh, my sensor triggers a camera to go take a picture. That is not a new concept. It's actually fairly mundane. It's actually how to use Internet of Things networks so that fiber optic arrays can be part of not just sensing, but actually analytics. And I'll share that a little bit more in the presentation. And then interoperability. It's not going away. It's a hard problem. Standards matter. So you'll hear me talk a lot about some variant of extensible markup language. Many of our companies that are part of FOSA have a good understanding of XML and how to get messages around in decent form. XML is great for some things. It's not for others. It tends to be verbose, and it's not lightweight, but it is out there. Some published standards are important for how does a sensor message from a fiber optic array, maybe enhanced with camera systems, maybe enhanced with millimeter wave radar, you name it. How do we feed information, alert information, appropriately into a common operational picture for enhanced situational awareness? And what does that integration look like, not only at the sensor-to-sensor level, but in terms of true fusion products? This is a hard problem. It's not going away anytime soon. People are constantly looking for elegance in that space. Something we work with a lot and have for a number of years is Sensor ML, an OGC open standard that is really important in terms of not just defining a message type, like, oh, well, we think it's this, and this is the time, and this is the location, but actually getting information out. And then metadata. I can't tell you how important metadata is about the alert, about the phenomena that's being detected. And you might want to be thinking about this notion of dynamic continuous metadata evolution, so that as different sensors across an IoT network are interacting together bidirectionally for advanced simulation and modeling and basically alert message structure, you might want to be thinking about doing that at the metadata level, which actually ends up being a much lighter way of analyzing data across blockchain structures, across encrypted structures, and make for very lightweight packaging. So that's just a lot of information that you're going to see spread out across my presentation, and I wanted to get that on the table for the audience members today. So I think the big things that we're faced with as IoT practitioners, and I really see our sensor system as part of an overall IoT security application layer, is this whole notion of how do we learn about environments over time, so learning algorithms, automating how machines talk to machines appropriately across different problem spaces. Obviously, fiber optic sensors are used in oil and gas, and they're used in pipeline safety, and they're used in pipeline security, and there's a lot of applications, border, perimeter, infrastructure, non-defense related. But I really think learning over time, automating the connectivity and the analytics, and then establishing effective communication. We learned a long time ago as a company that, again, very rarely were we able in a defense space to show up with our software application and have it be standalone. Very rarely did anybody in the government want us to just operate in a silo. And in fact, that's not a good way, at least for us, to consider our fiber optic array. So machine learning algorithms are becoming increasingly IoT-centric. They're becoming increasingly exposed in cloud architectures, both classified and unclassified environments. There's a lot of commercial stuff out there that you can leverage to some degree. Microsoft, Amazon, Google, IBM, some of the majors are definitely bringing forth their learning environments and making those available as services. But from a fiber optic perspective, when you're dealing with measuring things coming through the earth, etc., you need to understand that the environment drives so much of this phenomenology. You really got to have algorithms that are tuned into that environmental causation. This is what I mentioned earlier, the notion of dynamic continuous updates, so that we want to be thinking about iterative loops, so it's not just one-way directional, but we might detect something, we might get affirmation from another sensor, we may be queuing another sensor, the other sensor may be queuing us, we may be launching drones, you never know, UUVs, UASs, but the idea is, how do you have an algorithm that is designed for classification, detection, notification, for subtle analytics? How does that become something that can be dynamically, continuously updated, not necessarily in real time, but periodically in a way that you really are expanding? We spend a lot of time from an IoT perspective trying to achieve the following: detecting, classifying, localizing, verifying, and validating. The verification and validation of a phenomena is often when alert messages become important. You definitely are dealing with probabilities of detection and probabilities of false alarm rate and probabilities of this and that. So doing all that effectively across an IoT sensor networks is challenging and remains hard from a command and control or a C2 perspective. For those that know about fiber optic arrays, generally they're passive. They're not putting energy out into the universe, at least through the fiber optic cable. So you have the whole notion of how is the system, the dynamics of detectability of the sensor, the vulnerability of the sensor, and resiliency. And from an IoT perspective, when you're talking about machines talking to other machines, or virtual sensor zones talking to other sensors based on space-time correlation, you really want to be thinking about how your sensor can be described and shared to other machines so that the learning environments understand some of these dynamics. And then finally, as I've alluded to, automated analytics. We've got to be finding ways to let the machines and the sensor systems associated with those machines do a lot of work without having to have human involvement in order to reduce the burden on the human operator, reduce the burden of screen death, too many common operational pictures, too much situational awareness, and not enough effective messaging that allows people to know what they're doing. So automated analytics is more than Q to SLU. It is machine to machine, and then it's ultimately finding new ways to notify humans. So what you're going to see, as I've laid out all those sort of those concepts around IoT and fiber optic arrays and how they play into it, at least from our perspective, this diagram kind of gives you the area we play in, which is challenging, is never-ending, is dynamic. But when you bring a phenomenology into the world that is able to detect airborne surface and subsurface phenomena, you are bringing a capability and therefore a need that, again, we don't argue is a standalone, but is a component of a larger network-centric approach. And network-centric warfighting is not new, but methods and techniques for IoT, Internet of Things analytics is relatively newer, and it's hard to find good examples. But what I'll be showing you now in the next few slides are examples of dealing with detection, analytics, and different methods across these three domains. And by the way, I did not address cyber in this. That's a whole nother topic and lecture maybe I would do in the future. So to kind of get this into some case study level of analysis now for the audience, typically it's not a new concept to think of sensor as a service and then ultimately fiber optic sensing systems as a platform. It's a sensing platform that can play into some type of integrated application space. So what you're seeing here on the right on the images are screenshots of things where we are in the business of detecting things on terrestrial. For instance, that truck. What does that truck look like? How fast is that truck going? Can we get a license plate read on the truck? Obviously, we're not doing that with fiber optic acoustic. We're doing that by the right cameras being in the right place. So you're dealing with a lot of the things on the left, and I would highlight a couple areas in particular. IP6 addressable sensor arrays are very important. One thing we've done at our company, for instance, is when we talk about a virtual sensor that is deployed dynamically in the cabling system, we might be 2 miles out and it might be sensor zone 46. We actually work to make sure that that particular sensor, which might be 2 meters long and covering X amount of space and X amount of measurement, that individual sensor has its own IP address. So now you can start to see where the data and the sensor zone actually has its own IP6 address, and you can actually get very sophisticated and very fancy if you want about how that plays into hundreds and thousands of sensors, each producing a data stream, an analytic stream, and refining that specifically based on different automated needs and non-automated needs. So the tactical augmented reality is something else we're playing with, and I've mentioned this to my colleagues that represent technologists at the other sensor companies, but we spend a lot of time trying to go beyond the screen, go beyond the tablet, go beyond the phone, and those device types, which are very important, and actually try to translate sensor system information that has been aggregated up a chain, the whole notion of tactical analytics on the edge, and get that information in the easiest way for the warfighter so they're not having to carry another tablet, they're not having to carry another application, but it's integrated into their visual space. And augmented reality is not new, but it's getting popular, and it's important to integrate that into security forces and other people trying to have situational awareness about their geography. And I think this is something that fiber optic digital acoustic sensors can play a lot of. We have so much data we can provide. It's so rich that can provide a lot of information. So tactical augmented reality is important. Another example, again, you're going to sort of see this over and over again, is the importance of UX, UI flexibility, interoperability, and extensibility when it comes to how digital acoustic sensors play into IoT frameworks, at least in this case, of security and perimeter. But I don't think this is necessarily not relevant to the oil and gas market. I don't think it's not relevant to pipeline safety and security or any of those other markets, or even other uses of fiber optic arrays that we haven't discussed. I think everybody's looking for how the sensor can cost effectively provide the right information at the right time to the right operator or the right user or the right decision maker. So this screen are actual screens of how we interoperate with a forward-looking infrared, how we've operated before with a thermal imager, again, just sort of a high optical camera, a Google Glass environment, and then your more traditional get that information to a laptop or get that information to a desktop, often arrayed in network operation centers or tactical operation centers or some aspect of that. This is not new concept, and this is something that we do and other people do, but the challenge isn't just getting the messages to that application space through that standard, you know, a JavaScript or a JSON protocol or some other REST endpoint. The challenge is to do the analytics across your entire sensor network. So what I mean by that is, obviously, we spend a fair amount of time trying to figure out what something is and providing a high level of assurance that it is something relevant or significant and not something irrelevant or insignificant given the concept of operation. So you might have analytics going on the sensor array. You might have analytics occurring with other sensors. And you want to start finding ways to computationally achieve distributed analytics across your sensor networks, which can be both open and secure. And that's something that we spent a fair amount of time worrying about. I'm not going to say we have it all figured out, but it is something that our customers are demanding in terms of how the IoT network becomes more intelligent and smart. Now, one way we've done this in the past is through a relationship we've had over the years with our friends at IBM. This is a slightly technical slide, but we've worked with their real-time analytical processing software, InfoSphere Streams, in the past. It's now an open source code base. But when we did a lot of our work in 08 and 09 and 10, in our early days, you will have found me and others at IBM Research implementing this entire processing element container notion as a value add to our sensor array. The idea being we wanted an analytics conveyor belt. This is real-time analytical processing that would allow us to keep up with the volume and the rate, about 8 megs a minute and, petabytes or terabytes a day. This is not new to those in the industry, but there's a lot of data produced by these sensor systems. And typically the clients don't want to handle terabytes. We don't want to just collect it and analyze it later. So it's the whole idea of analyze it as it comes, but then be able to send the right information to the right other sensor without a human intervention to make sure that they may analyze it from their perspective. And you start to look at how that aspect of the electromagnetic spectrum can be analyzed in a distributed way. So this is just one solution. There's lots of other ways to do it. You can do a lot embedded. You can build smarter chip architectures. You can achieve things from FPGA. Software's getting cheaper. GPUs are getting cheaper, et cetera. But this is the notion of advanced classified cloud classification. So you can start to do some pretty interesting things with customers depending on their needs. Another example of a workflow, if you will, I'm not going to spend a lot of time on this. You can read this yourselves. We did get permission to share this. But, again, a lot of sensor types out there, a lot of investments. And that particular workflow was designed to basically help us study this particular area on the Earth. This was a secure area. We needed to provide a solution for a government customer dealing with road traffic, movement across a river. You had about a 2-mile area of interest, so it's a wide area surveillance problem. You got a lot of environmental noise. You got a lot of atmospheric noise. And what I wanted to share here with the folks on the webinar is we put in a small array, buried fiber optic cable represented by the blue line here near that river to the top of the screen. That's a riparian corridor. So we're down in a floodplain. There may or may not be bad guys trying to come across the river. There may or may not be, drugs coming across. You've got different vegetative areas. You've got, not an ideal situation. So we put in a simple array there, not very long, to basically create, an antenna, to create a sensor array. And why that was important is that in that situation, we started to see actually tunneling activity occurring, and we did some tests associated with that. And so why I'm showing you this next slide on tunnel monitoring is that oftentimes you'll find investments in tunnel detection and tunnel monitoring with very sophisticated other sensors, ground penetrating radar sensors, seismic sensors, super low frequency, heterodyne systems, you name it. And so the concept is that if you're going to be involved in that sort of persistent change detection, it might not be that you're detecting something as it's occurring, but you're going to be gathering data over a long period of time and basically trying to compare through, billions and billions of data points and obviously petabytes of data, what's going on over time, because that often will be the most significant way that you can look at not only tunnel formation, but also tunnel use. So again, you need to be able to reach out across your IoT network, and you might not be the company that makes the world's best algorithm for change detection based on this frequency modulation, but you want to be able to go out and get it when you need it and use it when you need it, and then not use it again. And that's important when it comes to this whole notion of analytics as an Internet of Things service capability. So you have analytics as a service, sensor as a service, platform as a service. You guys get the drift. Shifting gears here briefly, beyond sort of the border crossing and that sort of heterogeneous hard environment problem, Obviously, classic perimeter security problems require similar capabilities when it comes to surveillance, perimeter, understanding flexible membranes and flexible perimeters, and that they have to be ridiculously reliable. So certain clients, like the U.S. Air Force, has security force requirements that are hard. And it's very, very troubling for them when they get false positives and they have to dispatch people to places. Not only can that be a security threat, it's very costly. And so more work needs to be done always to try to find ways to refine and enhance. And again, this is another sort of standard example of where a fiber optic sensor system needs to be able to work well with not just other sensors, but again, what I'm arguing is that sort of that underlying analytics fabric that addresses change detection, focuses on not just classification, but actually enhancing the perspective over time. So time and space dynamics and geospatial analytics associated with our data in 2D, 3D, and often 4D space, especially for those companies that do good work in 4D seismic, four-dimensional seismic survey. Time can be a very important component, and oftentimes it's forgotten when you're dealing with real-time situations and things are moving very quickly. This is important for the audience that are not familiar with fiber optic sensor systems or digital, distributed acoustic sensors or whatever, to get an idea of leveraging the full electromagnetic spectrum when it comes to different problems. And again, I'm obviously focusing on the defense intel space, the U.S. space, but for those of us that don't remember the electromagnetic spectrum, I thought this diagram was useful. There are sensors, of course, that are in the infrared and the visible space. We rely and work with them a lot, so you can understand where they are in terms of 1 terahertz to 10 terahertz. A lot of stuff going on there. You can do some interesting work with X-ray and ultraviolet, especially depending on drug interdiction and narcotic smuggling and what's going on there. Of course, you get into the radio spectrum. Increasingly, we are doing work where our sensor is being used to correlate radio traffic, cell phone traffic, cell phone intercept. There's a lot of need there. There's a lot of stuff coming out of the government on that. The enemy is sophisticated. The enemy is losing. They're learning how to continuously evolve and defeat. They're very well funded. So you got to understand, how does this play into a larger play? I'm making the same argument. Then you get down into that sort of traditional 1 megahertz into 100 kilohertz space. We spend a lot of time in that frequency domain based on Rayleighs. My colleagues would be familiar with this in other industries and businesses. Increasingly, not new concept, but a lot of information from 10 hertz to 1 and from 1 to 0. Very low frequency work. And it's hard to have, any single sensor per se, depending on the ConOps or the concept of operations or what you're trying to achieve, to magically figure out and how to be dialed in perfectly for all those sensor ranges and all those frequency bands and all the phenomena represented by that. So what I try to do, and I do it imperfectly, is I try to think about the spectrum and what we're sensing passively and actively, and how we can collaborate with other companies and other sensors and existing investments that the client may already have. The clients often don't want to throw away hundreds of millions of dollars in investment, but they're looking for easier ways to plug and play new widgets into their existing sensor framework and their mission objectives, and do it with the least amount of money and the least amount of proprietary connecting fusion technology. So we spend a lot of time trying to make it easy to be connected and consumed into those existing investments and those existing sensor systems that are measuring different aspects of this, this optoelectronic array. Obviously, this is true. I'm not speaking as a company here, but I'm speaking as an observer of what's going on southern border, northern border. The operational control of northern southern border remains a challenge. There's been massive investments in both personnel and technology, and I say technology, everything from border structures and wall structures of different types, all the way up to very sophisticated, super expensive platforms. We see digital acoustic sensors and fiber optic arrays as being part of that matrix, part of that scenario, measuring things in 3D, 4D space, looking into and observing passively what's going on the other side of the border into Mexico and Canada within the smart border concept. Obviously, we believe that digital acoustic sensors, distributed acoustic sensors, can play a great role in this space, but you have to understand the heterogeneity of the environment, the heterogeneity of the geomorphology, the difficulties, and again, how you really need to leverage not only the appropriate sensor fusion and the Internet of Things architectures, which I think DoD offers a lot there, but also how do we create new ways of providing the information to the Border Patrol agent, the CBP agent, the DOJ agent, whatever, so that they are able to focus on their job, but also, again, give them really interesting, discrete visual experiences that allow them to do their job perhaps a little more easily. For those that are tracking border applications, this is sort of the example of the investments that have been made, that are being made, that will be made. And this gets complicated from an architecture perspective. It gets complicated from a standards perspective. It gets complicated from a scaling and extensibility perspective. This is, very, very large corporations are in this space, but you've got integrated fixed tower deployments on southern border. You've got emerging remote visualization sensing systems, RVSS. Those are pictures of the border wall prototypes, which may or may not have sensors embedded in them. Fiber optic sensors embedded or not. And then you've got vehicles, and you've got movement, and you've got GPS locations against various types of fixed border structures. So this is a really grand challenge. 2,300 miles of the southern border is not for the faint of heart, and the northern border isn't something to be laughed at either in terms of difficulty and terrain. So you might have the greatest sensor in the world, but you better know how to get the comms, you better have the power, and just when you get that figured out, you better know how easily and relatively effectively and cost effectively to add value and to other sensors, but more importantly, figure out where they are with their APIs, with their SDKs, with their plug-and-play architectures. Is it truly plug-and-play, or is it just a gimmick? These are all hard things. But that really gets into the ISR mission. Now, another thing I just want to share here as another sort of example, this is sort of a cartoonesque example of a real-world situation from a number of years ago. But this whole idea of really trying to get sophisticated about what we're trying to view, how we're viewing it, and what's that look like. So cameras all have fixed focal points. They all have camera fans. They all know what they can cover and how well they can cover it depending on range, the size of the target, the pixel dimensions. It just gets better and better all the time. So we've done examples where we'd have a target moving through a series of camera fans, and we needed to get just a picture of a license plate. So let's say something's moving from left to right on the screen. It's going down the road along the blue line, which is the buried cable. Camera fan A is represented by blue. Camera fan B is represented by the red and yellow pieces of pie. So again, not a radical new concept, but you can predetermine and preposition using geospatial analysis and the phenomenology of choice. And as that thing goes through, you can go after the validation and the verification and the identification of the threat target by trying to grab information. Now, this doesn't necessarily have to be a border app or a perimeter app. This could be occurring miles away from an area of concern. In the drug interdiction world, this may be something occurring, 25, 30 miles off border, still in a controlled area where you're doing observation. You may not be able to always do a checkpoint. You may not always be able to do roving checkpoints, but relatively inexpensively, you could set up something like this, and you can do some really good intelligence gathering. And so this is just an example of how we spend a lot of time worrying about camera systems and working with camera manufacturers to make sure that we can complement what they're doing and vice versa. I would not be able to do the presentation without giving some spectral analysis of what some of these target features look like. This is not new to anybody in the industry, but the idea to separate out what a human looks like walking and a UAV flying around is something we spent a lot of time doing at Adelos. But this is a spectral visualization of intensity against frequency against time. So frequency on the left, intensity on the right, and time. And, you know, we are pulling out these phenomenologies and measuring these frequencies at distance, at range. Again, to my point is, where's the analytical fabric for Internet of Things so that other algorithms can be applied now, not just to analyzing the acoustic signal or analyzing the FFT or the DWT, but where are we technically in terms of spectral feature analysis? There's a lot of data in there. And once that transform has been completed, you can do some really nice interdisciplinary cross-pollination, if you will, with other entities that are operating in the spectral realm and looking at spectral features and heat features and, you know, different aspects of that near IR or mid IR, and then link that up into comms channels, as I was showing you earlier. Not easy to do, not figured out necessarily, but something we worry about, and I wanted to bring that in to the discussion. Another example, another sort of cartoonesque DoD workflow, which I was able to bring forth, is this whole notion, and I'll go quickly here because I've already highlighted this a lot, but I want you to focus on these blocks of metadata. These are called metadata cubes. It's an idea we have that allows us to basically take location, probability to detect, time, azimuth, direction, and iteratively over time, all in network real time, basically go from a detection to a camera to a UAS deployment or a UUV deployment, it doesn't matter, or a surface vessel deployment or a robot deployment. But the idea being that we don't need to have 30 people analyzing all this to get the bird in the sky, to get observation on the target that is of concern. And you may not want to interdict, you just may want to gather intelligence. But you've got your center picture there with the threat dome, and you've got your layers of the onion, and, you know, we might be 20, 30 miles out from the problem. We always like to be places that no one ever thinks we are. And then you basically queue and you get these different things working together. But again, as I'm going to keep saying, I want to drive this point home. I would love to be thinking about how code and absolute analytical code and different algorithms can be distributed across these compute resources in different levels. Usually that doesn't happen from a vendor perspective. Everybody's got a solution, everybody's a stovepipe, everybody's got it figured out. But the standard for interoperability for analytics through IoT is very exciting. Because at the end of the day, you need to be able to do all this stuff to get the right information into these incredibly complex workflows where human beings matter, brain power matters, operational experience matters, law enforcement objectives matter. And, you know, where we are kind of as a society is we put a lot of screens in front of people. They're very geospatial in nature, trying to put the problem on a map, figure out where the problem is, how to get to the problem. But we're kind of stagnating at some level in this type of NOC or talk or fusion center. And we need to think about new ways to interact and new ways of bringing that forward. So to sum up here, and I'm going to leave enough time for hopefully adequate questions or comment with the FOSA moderators and host folks, I'll leave you with the following. Again, I still believe in the importance of system of systems. I'm kind of an interdisciplinary person, so I believe in sensor analytics. I've made that point, and I wanted people to understand it, as hopefully they do. Distributing the analytic load for sensor function is good and important, and what I wanted the FOSA community to understand and the webinar participants to understand. So let's join the phenomenologies together with relatively lightweight problems and work our way up, okay? Second, I think we need to improve the sensor analytic protocols. So we've, you know, worked with sensor ML. I'm a big fan of MQTT, CWG, interoperability, SEIWG, actually, I'm sorry, that's a typo on my fault. There's no I there. Look at the DoD standard for CWG. It's really, really important for interoperability. A lot of our clients demand that our sensor comply with and talk to CWG, and that's something that I think can't be said enough. It's not that standards don't exist, but when it comes to how fiber optic sensors play into these standards, at least in the United States, it matters. And global, it matters too. And then finally, I think digital acoustic sensor companies or distributed sensor companies could lead the way in a standard for exposing our rich data management capability, especially when combined with digital strain sensors and distributed temperature sensors, so DSS and DTS systems, Brilliant and Raman systems. We operate on Rayleighs, but I think there's a lot of technical expertise among the distributed acoustic sensor companies, as well as other collaborators and scientists and folks across the spectrum. I think we could do more there. Now, I'm the first to call for it, but I'm the guy that has almost no time to do it. So there is a little bit of hypocrisy in that last bullet on my part when it comes to bandwidth, and no pun intended. But I do think there's an opportunity here, because I think when you're measuring these kind of phenomena that we do using fiber optic arrays, you know, one man's noise is another man's intelligence. And I think it's so rich and so volumetric and so hyperdimensional that I think we can do a lot there. So I'm going to pause there now. It's about 12:41 Mountain Time, and I want to turn it back to my FOSA colleagues and collaborators and moderators, and be able to open it up for any discussion, any questions anybody may have for me, and I'd be happy to try to answer those to the best of my ability. So thank you.
Well, thank you, Dr. Philp. This is Mark Unkefer. If you would like to ask a question, the way to do it is there is a, on your right-hand corner, there is a text capacity to ask questions, and we'll take them in order. But let me take the prerogative of going first. I'm just staggered by frankly, the challenge associated with integrating all this data from a variety of sources. It would seem that really that's one of the real challenges to overcome. Can you elaborate a little bit on the standard setting process that you've encountered, some of the issues? I realize you're in the DoD space, but I'm trying to get a kind of better feel for how you've been able to overcome that battle.
Well, yeah, so thank you, Mark. I'm not going to say that we at Adelos have overcome the battle. I think we're battle scarred. Yeah, remember, we are a relatively small business, but we take on some really hard challenges for the DoD customer. We like that space. I would say that the Department of Defense has done the best in many ways as a government-driven organization because of the hundreds of millions and billions of dollars invested in sensors and acquisition, that whether it's Marine Corps, Air Force, Navy, Army, they needed to have ways in which when a new capability showed up at the fight, and let's just say sensor, and they needed a relatively easy way to get that connected in, so that we were de-emphasizing proprietary data structures, de-emphasizing proprietary this and that, but basically emphasize a layer of interoperability that not only was, hey, can this sensor send an alert somewhere? That's good, but can this sensor call the right analytics? Can this sensor connect with this other sensor? And so those interoperability standards, and the CWIG one that I referenced with the improper spelling, and I could follow up, that's known, that's published, it's out there. There's also the OGC standard, the Open Geographic Consortium that I mentioned, Sensor ML. We did a fair amount of work there in a loosely confederated way. There is an explosion right now in MQTT as being a really interesting messaging architecture around IoT. And obviously what's really driving the Internet of Things, which I think is, you know, a lot of hype as well. It's kind of like big data was 5 years ago. But I think beneath that, there's a real opportunity to figure out classes of sensors, and the commercial markets are really driving a lot of the interoperability standards for IoT. Now, we don't spend a lot of time doing the commercial stuff as much as we do the US government stuff because we don't have enough bandwidth. But I'm saying that when you have a group, when you have a sensor system like we do, and I say we, the general we, all the companies involved in FOSA, remember, we produce a lot of information. I think that's good. A lot of data needs to be converted to effective information, needs to be further refined and distilled down into effective comm structures, and then the right messaging structures. And I think it's an open area for innovation. I think it's an open area for anticipating the whole area of where cloud architecture is meeting information of things infrastructure, and then this whole idea of sensor as services. So I guess I'm repeating myself a little bit, Mark, and I don't know if I've added any more value to your question, but that's what I wanted to focus on today in my contribution to the FOSA webinar series, if that makes sense.
Sure. We do have one question about actually relative to tunneling, and it may be a more technical question, but while fiber optic sensing can detect tunneling, that is the activity of building a tunnel, is there a capacity to detect information about tunnels that may be active or actually inactive that are being used?
Yeah. So I can't go into too much detail on whoever's question that was, because this is an open line and I'm ITAR controlled, and I had to go through a lot of effort to just clear these slides that I presented to FOSA today. You guys know that. The short answer is yes, but how that happens, I can't get into. Sorry.
Okay. Sounds intriguing. Would you comment a little bit on sort of the next steps that you see for expanding the applications into the commercial applications? Do you see other players in this space?
Well, yeah. I mean, so as you know, Mark, there's a lot of folks involved in FOSA, and as FOSA is growing and we're doing a lot of advocacy, I would say that just because because most of my work is in the defense intel space, I'm saying that interoperability standards and sort of messaging structures and what I'm really hungry for is this whole idea of distributed analytics. I see that being very, very relevant in, let's say, commercial oil and gas, both upstream, midstream, and even downstream. We never lack. So what I always say is, okay, we've collected a lot of great data, fantastic, and we've done our own processing and we bring something to the fight. But I don't think you can ever not have enough smart approaches to analyzing the data to meet various business processes and various workflows. And different cultures have different demands on what they believe to be the figure of merit and what they're going to use to actually make operational decisions, whether it's deploying somebody or turning off a valve or realizing that $300,000 well, is not as good as you might have thought in that one exploration. So I think it's right for commercial. I think it's happening in commercial. And I think there may be some lessons learned, perhaps not perfect lessons, that we could draw from, the U.S. government investment in sensor analytics and data structures and common operational picture structures that may be beneficial. So there's kind of a best of both worlds. I know that the majors, the IBMs and the Microsofts and the Googles and the Amazons and others, through WC3 and other standards bodies, are really pursuing a lot of this when it comes to IoT. In the defense space, it's been there a long time because of how much there is and how much complexity there is. And I think out of that, FOSA can help lead the way or create dialogue with participants or members to try to, let people know what we're bringing to the table and how we can complement and add value to that discussion. That's my answer to that person's question, I guess.
Sure,
Yeah.
And actually the next question is a kind of a natural follow-up of what's the most important step that the federal government needs to take in order to facilitate more fiber optic sensing? Is it appropriations? Are there policy steps? Is there something else?
No, that's a good question. I mean, the federal government plays such a critical role, at least the U.S. federal government in this space. I would say that let me be careful here. I answer this, so I try to be intelligible. I would say it's not just throwing more money at stuff, although funding is important, but I would say it's say, hey, fiber optic sensing systems can play a role and do play a role and can play a role in helping our military industrial complex grow and evolve. And when I say that, the industrial interests and applications and military applications, that's important. And those industries are highly related in many regards. And so I would say I would look at it in terms of understanding. The government should understand and fully understand the limitations of the sensor systems and their capabilities, because they're not all the same and they complement each other, but they're different, but it's hard industry to understand. The second thing is focus on how they can complement existing investments in infrastructure development. So how we would complement smart roads, and how we would do smart car technology, and how we could play into, elements of medicine and aerospace and management of drone infrastructure and drone detection and in commercial problems and things up there. And then, so it's sort of interoperability on not just how the sensors can talk, but analytics, if that makes sense. And then the third area is find and create, bodies and organizations across multiple sectors, from transportation to defense to homeland, that would be coordinating and talking. Because I know there's a lot of money spent over here and here and here, but sometimes because of the information, it's classified or not or whatever, the government is not leveraging their unique individual investments into a holistic way. And I think what they want to do is look at the sensor phenomena, look at the standards, and then coordinate their funding if possible. Now, DoD does that to some degree. DHS does that to some degree. But I think we're relevant in the federal space to transportation. We're relevant to Department of Energy. We're relevant across a lot of federal areas of responsibility. And so I would create some type of committee, congressional steering committee, maybe some type of omnibus group that is looking at how to leverage this technology and the American investments and the foreign investments, because they're it's both, and figure out how to exploit that more effectively for taxpayer return. That's the bottom line here when you're playing with taxpayer money. Final point: explore public-private collaboration. So the federal government doesn't always have to take all the burden on. I think you'll see this as a constant theme coming out of the White House right now. How do we share that risk load? How do we come up with innovation? And I think a logical one is to look at the telecommunications industry and that investment in spectrum and data and analytics and broadband and fiber optic cable, and where are there appropriate areas where we could leverage those massive federal investments in telecom along with private investment and basically turn a telecommunications infrastructure into a sensing infrastructure. And that becomes very exciting. It's not easy, it's not trivial, but it's definitely something to explore, if I make sense. Yep.
Another question has to do with, as you're integrating this sensors with different characteristics, would you comment on the sort of the time framework? That it would seem that in many use cases, the fiber optic sensing is going to be much quicker and much more immediate in the kind of data that it can provide. Is there a time lag? Are there issues associated with that when you're trying to integrate?
Yeah, that's a great question, whoever asked that. Yeah, obviously, for those of us in the DAS space, fiber optic sensors, and hopefully there's some of my colleagues from other companies on the line. But yeah, we produce things that happen fast. Other sensors may not be that fast, and that's okay. And so it's not necessarily that everything has to be so-called network real time over 500 miles or 2,000 miles. And oh, by the way, there are lags on comms. Photons are photons, and I can't go any faster. And if I'm measuring something over here, but I'm analyzing it 3,000 miles away or 8,000 miles away over here, you have lag. Now, because so much has been done in remote control and remote visualization and flying a UAV out of Las Vegas, but dropping targets in Afghanistan, there's ways to look at our communications infrastructure and our delays regarding command and control and other things. So what we also found, if you're doing like IED detection or other things, or even like I said earlier about tunnel detection, it's not always you got to have everything done instantaneously. You may observe something for 6 months, especially given ambient background noise and a whole bunch of perturbation events, and you're really trying to pull out subtle things. So it may be forensic in nature. You may need to go back in time to a recording and be able to link up through the common denominator of GPS time. Well, what did we see there? What did we hear there? What's the human then? And you can start to pull together a more sophisticated thing. I find a lot of times people want silver bullets and magic bullets, and they want to get it figured out. But sometimes these problems are hard, and so you need to be comfortable with both connecting things in real time, but also being able to go back and sort of dissect and analyze, you know, in the past in order to better understand the future. So everything operates on a different tempo, on a different scale. We have different networks, and it all depends on the tempo and the problem you're trying to solve, would be my sort of simple answer to a really good question.
Good. Well, we're coming up to close to the hour, so I think we'll probably stop right there. I will say that we're going to be having another webinar, so thank you very much for a very informative discussion about an area that we really haven't spent as much time with in FOSA as we will in the future. Your presentation will be up on our website probably tomorrow. It will also be available on the FOSA YouTube channel, which is another way to access that information. Next month, in March, on the same day, March 15th, Thursday, we will be having a webinar with Omnisense. We're just still in the process of putting together the description for it, so it's not something you can register quite yet, I don't believe, but you will be able to do that shortly. So, Doctor, thank you very much for a very informative presentation.
Hey, thank you very much. I appreciate the opportunity. It's great to be part of FOSA, and I hope that the webinar participants got something out of today. Thank you very much for the opportunity.